It's a pleasure to introduce one of the young and talented speakers. And this is Mikael Rechtsman from Penn State. He's going to speak on
Photonic topological insulators. Okay, great. All right, well, thank you very much, and thank you to all of the organizers for having me. And I'm very, very happy, as are many of the speakers, to be here on the occasion of Michael's birthday conference. We've never formally collaborated exactly, but I've been really very proud to have him as a friend, and I really, really enjoyed all our discussions and conversations. So congratulations and Mazal Tov. The first time I was in this room actually was on a grad student visit, a grad school visit to Princeton. And I noticed that we were having some problems getting the lights dimmed. It was exactly the same situation. Everyone was sitting there and there was some biophysicist giving a talk exactly here. No one could understand his slides because it was completely drenched by light. And so they asked a grad student to go up and turn off the light somewhere. This was not here at the time. So the lights were not controlled here. The grad student ran up and sort of came back and said, I can't find it. Where's the light switch? I said, okay. They sent up an assistant professor. He went up and he came back. He had no idea. And it went up through the ranks. So it went to some associate professor, and then a full professor, and then a chaired professor. And then there was a Joe Taylor, I think, who was a Nobel laureate, went up and he tried and he came out and he really had no idea. And then finally, someone said, okay, well, send Ed Witten. And Ed Witten was in the audience and he went up and he just had no idea. And so we just all listened to the talk. We couldn't see what was on the slides, but they proceeded anyway. So I thought, wow, this is a special place. I have to come here for grad school. So anyway, so let me get started. The title of my talk is Photonic Topological Insulators in Propagating Structures. This is work that was largely done when I was a postdoc in Moti Segev's group at the Technion in Israel. And it's a collaboration with the group of Alex Samite in Jena in Germany. So you may have heard the term topological insulator. This talk is intimately related to what Charlie Pfefferman was talking about earlier today. This is an absolutely major research topic in condensed matter physics, absolutely major. It's, I would say without much exaggeration, that a third to a half of condensed matter physicists are working on systems like this. So you're talking about a March meeting with, I don't know, on the scale of 5 to 10,000 people, and something like half the people are working on this type of new material. Both because they're really, really fascinating, they have these deep topological properties, and because of some interesting device applications that I'd be happy to talk about, essentially having to do with extremely robust flow of electricity. So what are they? They are materials that have a bulk band gap. So that means that they are insulators. That's what makes them insulators. But they have states that cross the band gap and reside on the surfaces. Or if you're talking about a two-dimensional material, the edges. And those states are completely scatter-free. So that means that if you have an electron wave packet that's propagating along the edge of a two-dimensional topological insulator, then if it encounters some form of defect or disorder or this dopant or whatever it is, some sort of defect, it simply passes through it without scattering whatsoever. And the reason for that is actually relatively simple. So if you think about just a standard one-dimensional scattering calculation in the Schrodinger equation, you have some sort of barrier. You know, you set up an incoming wave, transmitted wave, and a reflected wave. You match up the boundary conditions, and you get T and R, transmission and reflection, as a function of frequency. But if you don't have a reflected channel, or you can't access it for some reason, then you simply have to have that the amplitude of T is 1. You have to have perfect transmission through the structure. And that is what accounts for the robustness. So I've been asked whether this topological insulator physics is just a very, very fancy term for impedance matching, because you get perfect wave transmission. But it really is not, because this barrier can have any shape whatsoever. It can be any kind of wobbly thing. And you would always have perfect transmission, no matter the shape of the barrier. Of course, the hard part is doing this, is how do you eliminate that reflected channel? And so what you have to do is to break time reversal symmetry, because time reversal symmetry in the Schrodinger equation tells you that if you have a solution that propagates to the right, then you can just take its complex conjugate and you have a solution that propagates to the left at exactly the same energy. So you have to get rid of that. You have to eliminate the reflected channel. If you can eliminate the reflected channel within some energy band, then you will have this property. Okay, so the first topological phenomenon that was discovered in the context of solid-state physics was the quantum Hall effect. Von Klitzing didn't know this at the time, but he was getting such incredibly robust values of the conductivity because of this non-scattering mechanism. He was getting 5, 6, 7 digits of accuracy in these Hall conductivities. You know, this is from sample to sample, from day to day, which is very, very unprecedented in those types of systems at the time. And so he thought of this as metrology. He was getting such accurate values that he actually called this paper, instead of the quantum Hall effect, new method for high accuracy determination of the fine structure constant based on quantized Hall resistance. And it came down, as Thales and collaborators found out later, to this non-scattering mechanism. So my goal, one of my main goals in my 2-month-old research group at Penn State, is to be able to bring topological physics into optics and to understand the implications of that, both on the fundamental physics side and on the application side. So there's all these incredibly complex networks in silicon photonics and fiber optic networks and what have you, so many different optical devices out there, industry upon industry upon industry. And these are fabricated structures, and so there's always random scattering due to fabrication disorder. And so the idea is, can we use these sophisticated techniques from physics to suppress that random scattering and therefore decrease energy requirements or increase signal-to-noise ratio in all of these complicated photonic devices? So that's the kind of technological vision. From a more fundamental point of view, optical systems can be seen as kind of analog simulation tools of usually condensed matter problems that can't be addressed in solid state, because solid state physics, you sort of have the lattice that you can grow, or that you can make, or that God has given you, and so you don't have that much control over what the exact system is, whereas in optical systems, we can just fabricate a structure and test all of these really neat theories that might have been proposed originally for condensed matter physics. So there's a number of systems that do that same sort of thing. There's ultra-cold atoms in Bose-Einstein condensate physics, cavity and circuit quantum electrodynamics, exciton-polariton condensates. Those are sort of the main other players. Some advantage of photonics is that we can pretty easily get topological phenomena, although now that's true in ultra-cold atoms as well. We can do entangled photons in many body states. We can look at strong interactions through the optical nonlinear response of the material. Sorry, I'm in your way, Michael. We get this sharp edge physics. So in ultra-cold atoms, you sort of have this diffuse quadratic trap. You never really know where the atoms stop, right? Whereas we just stop the structure and we have a sharp edge. So we can address that question that was asked earlier today about what happens when you just terminate. And we can have tailorable disorder in the sense that we can look at all sorts of different kinds of disorder because we just decide what it is when we fabricate the structure. So this idea originally of photonic topological protection originally came from Duncan Haldane and his student at the time, Sri Raghu, who's now a faculty member at Stanford. They said that if you take a photonic crystal structure, which is a structure that varies periodically in the plane, where the lattice constant, it varies in refractive index periodically, where the unit cell size is roughly speaking the wavelength. But instead of making it out of an ordinary dielectric material like glass or silicon, you make it out of a material that has a magnetic or Faraday response. So the permeability tensor for Maxwell's equations has this these off-diagonal terms here. Those serve to break what in optics you call the Lorentz reciprocity, but in solid-state physics you would call time reversal symmetry. So this breaks the time reversal symmetry of Maxwell's equations, these terms here, these matrix elements, and as a result, you at least set up the necessary conditions to be able to get these one-way states. And then in Marin Soljačić's group, they actually realized this in the microwave regime in a photonic crystal. This is a picture of it here, actually. You can see the unit cell is about the scale of 4 centimeters. So this is a thing that is about this big. It's really, really heavy, but you can pick it up, and that's the scale of it. So we're not talking about optical devices. We're talking about microwave response, basically because you can get this very, very strong, these very strong magnetic effects. In other words, you have a strong Faraday or Verdet constant. And so that's what they showed in a beautiful paper in 2009. But as these guys, Landau and Lifshitz, said, there is no meaning in using the magnetic susceptibility from optical frequencies onward, and in discussing such phenomena, we must put mu equal to 1. In other words, we are not going to be able to take the mechanism that Haldane proposed and just scale it down to optical wavelengths. Optical wavelengths are, roughly speaking, half a micron, so many, many orders of magnitude smaller than the wavelengths that correspond to microwave frequencies. Okay, so we're not just going to be able to take that magnetic mechanism that Haldane proposed and scale the whole thing down so we can do this with optical devices. We have to come up with another idea for how to do it. And so there were many different theory papers proposing different ways that you could sort of do it or halfway do it or do it but using some sort of scheme that was experimentally ridiculous and so on. So what I will talk about is our mechanism for how to do it and our experimental realization of it. The big central question is, how do we strongly break time reversal symmetry in optics? So that's the central question at optical frequencies. How can we break that time reversal symmetry? That's the difficult, tricky component. So before I answer that question, I will talk about the specifics of the experimental system that we use. So we use a fabrication method called direct femtosecond laser writing, where we take a pulsed laser, we focus it to a tight spot into a piece of glass. The glass sort of locally burns and melts and reforms at the spot of the laser, at the focus, just because of the sheer intensity of the beam. And when it reforms, it has a slightly larger refractive index. In other words, it forms a potential well. And then if you drag it along throughout the length of the sample, actually you drag the sample, right? Then that forms like a whole wire, or in optics you call that a waveguide. And then you do it again and again and again, and you can get a whole lattice. So what you have here is a lattice of waveguides with each one is single-moded, and each one is evanescently coupled to its neighbors. So in other words, you can have hopping from one to the next. Now the way you describe the diffraction of light through such a structure is actually by a How about now? Yeah, okay. So the way you describe the diffraction is using the Schrodinger equation. So I will go through a derivation of how you arrive at this Schrodinger equation from Maxwell's equation, time permitting later on. But this is a well-known trick in nonlinear optics. The way you do it effectively is you start off with an ansatz for the electric field, which has a carrier envelope type form. So this is a carrier wave. So this is the envelope wave, psi, and this is a carrier wave. The carrier wave is oscillating very quickly in the z direction, and the envelope wave is oscillating very slowly in the z direction. So if you make this approximation, then you arrive at this Schrodinger equation for the diffraction of light, except where the z direction takes the place of the temporal coordinate. So you can really think of the transverse plane as being a two-dimensional quantum system where the z-coordinate acts like time, effectively. And as the wave packet propagates through the structure and spreads, if you only look at its behavior in the plane, then you can think of it as obeying Schrodinger dynamics. So you can see this is a honeycomb lattice here. And so in the z direction, yes. So it's coming in the z direction, exactly. So this is a honeycomb lattice. So if I just take a beam of light and focus it into one waveguide, and then say I could track it as it propagates from one waveguide to the next, it diffracts through the structure, then the behavior of that photon going through is identical mathematically to if I had taken a sheet of graphene and put a single electron and watched its quantum wave function spread from one site to the next. Yes, Gideon.
I know you may comment on this in a moment, but you've got your delta index of refraction with a z dependence.
Yes.
So how do you fabricate a lattice that's also going to have a longitudinal variation?
Right. So that is going to be an important part. But essentially, you can do whatever you want with this thing because you're moving the sample. So if the beam is fixed and you want to have any crazy z dependence, you can think of it kind of like a 3D printer or something. You can make any pattern you want. Right. Okay. So let me give a sort of another schematic diagram of exactly what's going on here. So the wave is incident in the z direction. Now imagine I excite an edge here. If I see the light stay confined to the edge and say it moves to the right, then I know I have an edge state because it hasn't diffracted. Whereas if it diffracts and fills up the whole bulk, which is what usually happens, then I don't have an edge state for those conditions. It's as simple as that. Okay? Here's a top view. Okay? I see the wave moving off to the right. It's just a top view of exactly the same thing. Now imagine along the way, one of these waveguides acted like a defect. So maybe it had the wrong refractive index, or it had the wrong position. Oh, this one works? Okay, so let's switch again. Okay. So say it had the wrong refractive index. Then what you would expect is to have some scattering because of that disorder. And since T is now Z, then backscattering would look like that. Okay, so that would be backscattering in the transverse plane. Except if you have this topological protection mechanism, which I haven't said how to realize yet, then that channel is not there, and so you would just see the light propagate through. So experimentally, that's what I am trying to access. That's going to be the experimental signature. Okay? So how do I strongly break time reversal symmetry in optics? Well, now I don't have to break time reversal symmetry because my time coordinate is now z. So all I have to do is break z reversal symmetry, and I can have this effect. And so the way we do that is to make the waveguides helical instead of being straight. So this is a schematic diagram of the helical waveguide array. Here you can't see the helicity, but this is a microscope image of an actual sample. Now, if you take the Schrodinger equation and you rewrite it in a coordinate system that is co-moving along with those helices, because they're very, very adiabatic, then you recover a Schrodinger equation in that new coordinate system, but the Schrodinger equation has picked up this vector potential, or gauge field, here, A. That gauge field is dependent on z, meaning time. It is not dependent on x and y. So the curl in the plane is 0 here. So that means there's no magnetic field. But there is an electric field, a fictitious force that's acting on these photons that is time dependent. And actually what it corresponds to is just a force that's just rotating like this in time. It's not a centrifugal force or Coriolis force, because that would be if the waveguide array were spinning like this, right? And that's subtly different than doing this, right? In this case, the velocity of all the waveguides with respect to z is all the same. And so you get this fictitious force that's going in a circle. So now you have a Schrodinger equation which has a time-dependent Hamiltonian, and you have to solve it using the techniques of Floquet theory, essentially. Because if you have time-dependent Hamiltonian, we have to solve for the Floquet map and diagonalize that way if we want to get the eigenvectors and eigenvalues, if we want to get the spectrum of the corresponding operator. But once we've done that, then we have all of the ordinary machinery of a standard Schrodinger problem. This is related to ideas from condensed matter physics that were discussed in Eugene Demler's group and Gil Rafael's group. Michael?
Does it matter how slow or fast you twist?
Yes. Oh, yeah.
So what's, yeah.
I'll wait to you.
Does it matter how slow or fast you adiabatically vary the?
Yes, it does, absolutely. Essentially, you have to be, or the regime that we're in, and the important parameter to consider is that the pitch of the helix is on the scale of the coupling length between the waveguides. The length it takes for light to go from one waveguide to the other. Effectively, yeah. And you have to be, that ratio has to be roughly 1. Okay. You can also come up with a tight binding model, I'll discuss that time permitting, where you can essentially incorporate the helicity by adding complex hopping parameters between the sites on the lattice. So that's this here. I will very quickly go through the derivation of the paraxial equation. Yeah, Jianfeng.
For the experimental setup, is it really like hopping on the lattice? So it's really like a tight binding model, or it's so you describe them using Schrodinger equations, but should I really think of them as tight binding?
Well, the exact is the full Schrodinger equation.
Sorry, can you repeat the question, Mikael? Can you repeat
oh
the
yes,
question?
I will. Okay. So the question is, how do I think of the experiment? What's the actual physics behind it? Is it a tight binding model, or is it the full Schrodinger equation with Laplacian plus V? Is that what you're asking?
Yeah, because I mean, you mentioned that these packets will only kind of hop to next neighbors of these optical fibers.
Yes.
So that's, I mean, it's kind of like hopping already.
It is hopping, and so that's why the tight binding model. So the question is, it's just like hopping, so is the actual physics the tight binding physics? And the answer is that the full Schrodinger equation really does describe this system exactly in the paraxial limit. The tight binding approximation is just a very good approximation to that. So that's why you see it hop very straightforwardly. It's just a very, very good approximation, but it's not exact. And actually, we've done experiments where we see those differences have dramatic effects. Okay, so quick derivation. We'll start with time harmonic Maxwell's equations. Vector identity, plug that in. Here's another vector identity where we just expand out the fact that the divergence of D is 0. And then rearrange that, and we get this nice expression for the divergence of the electric field. If we plug that back in to the full Maxwell, then we get this whole wave Helmholtz type equation. It's just that we have this extra term here. This term goes away because the refractive index actually varies very slowly on the relevant wavelength, the relevant length scale, which is the wavelength. So for these particular structures, this refractive index change is quite low, and since we're talking about derivatives of that refractive index profile, and it varies very slowly, this term drops out. It's about a part in 1,000 roughly. And so now we're left with really a kind of a vector Helmholtz equation, and now we make this carrier envelope approximation. If we plug that in, then what we find is that we get a transverse Laplacian term, and then we get this standard solution to the homogeneous Helmholtz problem, so that goes away. So that's just a standard Laplacian in the transverse plane. These two go to 0 together. These go to 0 together. This second derivative in z, compared to this term here, remember that psi slowly varies in the z direction. So 2 derivatives of psi in the z direction is less than the wave number associated with the carrier wave times only 1 derivative in the z direction. So this is the carrier envelope approximation. This term goes to 0, and we're left with the Schrodinger equation. So that's justification of the derivation of the paraxial Schrodinger equation. How do we get the gauge field through helicity? Well, we just change coordinate systems, the coordinate system like this. We have the original Schrodinger equation, and we're just going to write it in the primed coordinate system. This is just a standard rotation that we're co-moving with those helices that have radius r and spatial frequency omega. And so if we do that coordinate system, the Laplacian doesn't get changed at all. The z derivative does get transformed. If we do a quick completing of the square in the Schrodinger equation, then that's how we pick up the gauge field. And so it's a very simple, straightforward derivation of how to get the gauge field from just this coordinate transformation. And there it is. Floquet theory, just a quick overview of exactly how we do this Floquet stuff. It's essentially just using Bloch's theorem, but in time instead of space. So we assume that the wave function comes back to itself modulo a phase after a whole period. And that phase is essentially the quasi-energy, or essentially the Floquet eigenvalue of the system. The way we do it in practice to find those eigenvalues is to calculate the propagator through one whole period of the evolution, and then diagonalize that unitary operator. When we diagonalize that unitary operator, we get eigenvalues on the unit circle. If we take the log, then that gives us essentially Floquet energies. Or we could take the log of the matrix to get an effective Floquet Hamiltonian. That's just standard Floquet theory. That's how we actually solve out the system. So what did the spectra actually look like? There's the honeycomb lattice. This is the case where the waveguides are straight. It's the honeycomb lattice, so as Charlie Pfefferman was saying earlier today, there's two elements in the unit cell, and so that means you'll have two bands in the band structure. Some of you may have seen this before, or recognize this as the band structure of graphene. It has these diabolical or Dirac points at each of the Brillouin zone vertices. The minute you make the system helical, you make those waveguides helical, that breaks the time reversal symmetry. That is known from graphene physics to break the degeneracy of the Dirac points. It opens up a band gap, and so that's what the spectrum looks like after you make it helical. Now you can actually solve for what happens on the edge by taking a unit cell that's large in the y direction and periodic still in the x direction, so you take into account the terminations. And what you find is that in the case where the waveguides are straight, you have these edge states that Charlie was talking about earlier that are completely dispersionless and flat here. So they exist. This is for the zigzag edge. They exist, but they're not going anywhere. Whereas the minute you make these waveguides helical, the band gap opens, the edge states go from being flat like this to going like this. So meaning the one on the top edge is going to the left. It has negative group velocity. The one on the bottom edge is going to the right. So in your coordinate system, it's like the top is going this way, the bottom is going this way, and it forms one whole part of one edge state that's going counterclockwise around the whole system, like this. There is no clockwise state. That's the one-way state, and that's the reason that you can't have scattering, because you only have a state that moves all the way around the system. The really nice thing about these topological systems is that the shape really doesn't matter. The type of edge doesn't matter. It doesn't have to be like a big rectangle like this. It can be some sort of crazy blob. You will always have a group velocity. You will always have an edge state that goes chirally around the structure, and you'll have this no scattering behavior. Yes?
The flatness is really a tight binding artifact, right?
The flatness is absolutely tight binding. That is 100% sure. Even if you have next neighbor coupling, then you will have some dispersion here. But what you won't have is states that just cross the band gap in the continuum. So to really cross the band gap, you have to have this topological nature. Here I'm just writing down, I'll just go very briefly through this. I'm just writing down how I can arrive at a tight binding theory from having a gauge field, right? So this is a standard way of writing down a coupled mode theory from the full Schrodinger equation. What you do is to expand that Schrodinger equation, that as actually the full continuum thing, in a basis of bound states of each waveguide. And that's how you arrive at this simple discrete Schrodinger equation. If you have a vector potential, then it's straightforward to make this what's called U1 gauge substitution. You take away that A of xy in general, A of xyz actually, by doing this, and then you can basically use this equation to arrive at a discrete model for the Schrodinger equation that has these now complex hopping terms. Okay, so now I'm going to show time domain continuous simulation. So these simulations do not rely at all on the tight binding model. This is the full Schrodinger equation being evolved. The array is sort of roughly a rectangle here. And again, these are simulations. These are not experimental results yet. So here you have a whole array. Okay, there you go. You see it move. It's hitting the corner now. So you might expect some backscattering along the top, some continuation along the edge, and then some scattering into the bulk. But what you see is it just continues along the edge because of this robust topological protection. The wave packet will just sort of do that forever. And so this is really the mechanism that gives those robust conductivities in the quantum Hall effect.
Now, if you didn't break time reversal symmetry, you would still have states which are localized along the edge.
Yes.
You would just get them going in both directions.
Absolutely, yes. So we've seen them. You don't even have to necessarily get them initially going in both directions. You can excite the one that's going to the right. It'll hit the corner, and then a lot's going to come back, basically.
But nothing into the bulk.
Nothing into the bulk, and nothing down along the other edge. So that's actually an important point. You don't, along the side edge there, that's called the armchair edge. In graphene, you have no edge states associated with that termination. And that would be true if our waveguides were straight, but because the light has to go somewhere, you actually find that you do form edge states on the armchair edge if you do have this gauge field, this topological protection. Here are the experimental results. So we cannot image directly into the array. That is not possible. But we can look at what happens at the output, and then we can change the initial conditions and see how the output conditions change accordingly. And so if you think of this red ellipse as a schematic of the input beam, and then this green ellipse as a schematic of the output beam, essentially what we're seeing is that. We move the input beam, and we see the output beam having moved around the corner and gone down along the side of the armchair edge. And that's what you're seeing in these experimental results, that we're moving the beam, the input beam along the edge more and more and more to the right, and then we see the output beam go farther and farther down along the side edge. More experimental results. Here we're not as interested in seeing the non-scattering behavior. We'd like to show the dependence of the group velocity on the helix radius, just to show that we get agreement between theory and simulation. So for purposes of this experiment, we use a lattice that's shaped overall in an equilateral triangle, input the beam to the top left corner, and what you see is that largely the light stays where it was excited. This is for the case of radius 0. In other words, the waveguides are perfectly straight. And the reason it stays is because those group velocities had no, those edge states had no group velocity in the case where the radius was 0, in the case that the waveguides were straight. And so the fact that they don't move is not surprising. It's 0 group velocity. But now let's look at different samples and increase the helix radius. And what you see is it starts to move to the right, wraps around the corner without scattering, and then gets really far. But then for larger and larger radius, actually the group velocity decreases and then reaches 0 again. What we found is that if you go back to the model and calculate what this is actually supposed to look like, what the group velocity is supposed to do as a function of helix radius, it opens up and then closes again. And so the band gap, and actually you get very good quantitative agreement here, which for tight binding models doesn't usually happen, but in this case you do. So the band gap really opens up and closes, and so in the language of topological physics, as long as it stays open, it has a constant Chern number, and then when it closes, you get a sort of ripping, so I'll talk about this in a second. And the minute it closes, the Chern number changes actually to -2. So I have an animation of that, that effect. And so let me just find this thing. So here is the groove velocity as a function of helix radius of these edge states. So this is the whole spectrum as a function of helix radius. You see it open there. So it's just this one edge state which is going to the right along the top, to the left along the bottom. And now it's going to close, the band gap's going to close, and it's hard to get exactly that point, but you see now there's two edge states and they're going the opposite direction. And this sort of pattern goes on forever. It's extremely rich. Just open and close as a function of helix radius. Okay. Okay. So let me go to the next slide. This is another experiment in which we purposefully left out a waveguide along the edge. So that acts as just a big defect. And then what you see is if we inject light on the top right, it comes down, goes around the defect, goes through without any scattering at all. So that's sort of a total of 3 experiments showing this effect. And in a theoretical work, we showed that solitons could exist in this discrete model within the topological bandgap. Those solitons we found could be close to stable, but they are not actually stable. But they can potentially be very long-lived. They are Floquet solitons, so they do have time dependence. These are actual animations, and this is 2 families of such solitons. We have sort of a tenuous interpretation of the solitons as being self-induced topological edge states in some sense. So they by virtue of the interaction, they induce their own potential well in which they themselves live, and they sort of live as edge states within that self-induced potential well. But it's hard to say whether they're really edge states or not. So that's sort of a bit of a hand-wavy interpretation.
This is where you have the coiling of the waveguides?
Yes.
So they're just going in one direction?
Yep, exactly.
So it's like, but that nonlinear Schrodinger equation doesn't look like it has a gauge field in it.
It doesn't. That's right. There should be a gauge field. Sorry. So I was just sort of writing the nonlinearity generally. But yes, it does have a gauge field in it. Yeah. Okay. And so I want to emphasize that the place where I think this field is really going now, this field of topological photonics, which now has maybe 10 or 20 groups that are involved in it, is in the direction of nonlinearity. No one yet has shown a nonlinear topological structure. It's very hard experimentally to do that for a number of different reasons. And there's a ton of interesting questions there and a huge community interested because the nonlinear Schrodinger equation is exactly the equation that you get in a Bose-Einstein condensate when you have interaction among the atoms and you're in the mean field limit where you have many, many atoms in the system. And in the Bose-Einstein condensate community, they've just been able to recently realize topological physics. And so a lot of people are asking the question, what are the effect of interactions? In other words, what's the effect of the nonlinear term? The equations are identical. It just comes down to this sign, whether this is a plus or minus, effectively. Whether it's a focusing or defocusing nonlinearity, or in the language of Bose-Einstein condensate physics, is it an attractive or repulsive interaction? Now, I do want to talk briefly about what it means to be topological. So this is a question that Charlie brought up earlier. And so I will just present the absolute simplest possible model of a topologically non-trivial system in this sense, which is a dimer model. So it's a model where you dimerize a 1D integer lattice, like this. This has a topological variate associated with it. When you dimerize that lattice, a band gap opens up in the spectrum. You can dimerize in another way. So you dimerize in the opposite direction. You can see here, in both cases, the bulk is exactly the same, but the edges are different. So if you start the unit cell with an edge, then you see you have a short bond and then a long bond. But on this side, you have a long bond and then a short bond. You would think that that wouldn't be relevant if you're doing a bulk band structure calculation where you assume an infinite structure. But it turns out that if you do the bulk band structure calculation, then there's a certain quantity which is sensitive to whether you have short-long or long-short. And that is exactly this topological index, gamma, which is called the Zach phase. This is exactly a Berry's phase, but where the adiabatic parameter that you're varying is the block wave number k. You calculate that quantity, and what Zach essentially showed is you get gamma in this case, short-long. Gamma equals 0 in the short-long case. Gamma equals pi in the long-short case. And that corresponds to whether or not you have a localized state on the edge, whether or not you have an edge state. So in other words, there's what's called the bulk edge correspondence principle, and that tells you that if you have this topological invariant that you calculate, which only changes when a band gap closes. In other words, there's some rip in the structure to sort of turn it from a sphere to a donut. So this is just obviously just a donut going to a coffee cup. So this is the band gap not closing, right? But if you have the band gap actually closing, that is a rip that can change the topology, which can change whether or not you have the edge state. And non-zero topological number is always associated with having an edge state, or at least having an interface between a system with non-zero topological number and a system with a different topological number, which could be 0. In two-dimensional systems, that exact quantity is called the Chern number, and it is, again, exactly this Berry's phase where the adiabatic parameter is k, the block wave vector, and you integrate around the whole Brillouin zone. And so in our system, all we had to do was take the bulk band structure, calculate this quantity, not resort to any edge physics at all, calculate this quantity, and say we get Chern number 1, which is what we get in our system. That tells us that we have one edge state along the edge, and it's chiral in the sense that it'll just propagate counterclockwise without scattering. So as I mentioned before, I think a major challenge of the field is the question of what happens with interactions. And this is a natural direction for us in the physics community to go, and also a natural direction, I think, for people in the mathematical community to go, and applied math community for those who are interested in more rigorously understanding topological insulator physics. The question is, what about interactions? Now, depending on how much time I have left, 5 minutes. Okay, good. I think I can do it. I'll just talk about another project that we are finished and that we've submitted, and that is topological transport in photonic quasicrystals. So what is a quasicrystal? It is a very, very unique material. It exists in nature, and it was discovered in the early 80s by Danny Schechman. Effectively what it is a material that is definitely crystalline. It has long-range order. It has these Bragg spots associated with its X-ray and electronic scattering spectra. So it's definitely crystalline, but it has no repeating units whatsoever. So there's no unit cell at all. But it does have symmetries, and those symmetries can be non-crystallographic. So this structure here has 5-fold rotational symmetry. So as you know, you can tile the plane with squares, you can tile the plane with hexagons, but you cannot tile the plane with pentagons. So this system could never be periodic because it does have 5-fold rotational symmetry. And this is sort of the fundamental model of a two-dimensional quasicrystal. It does have that symmetry, so it must have long-range order, and yet it has no periodicity. Why are quasicrystals interesting from a physics point of view? Well, the wave transport is really strange and interesting because you don't have a wave number. You can't precisely define Bloch's theorem. There is no Bloch's theorem. So it really makes us rethink wave physics in a way, and transport, what transport means. From a more technological point of view, quasicrystals can be shown to have effective Brillouin zones. For a Penrose tiling, the Brillouin zone is a decagon. And so it's very, very close to being a circle as compared to the most circular type lattice, which is a triangular lattice, which has a hexagonal Brillouin zone. So it turns out that the more circular your Brillouin zone, the larger your band gap can be, your photonic band gap can be if you're looking at low contrast materials. And that includes materials such as self-assembling polymers and colloidal structures. So if you ever want to have a self-assembling band gap material, where instead of doing very, very expensive fabrication, you can take some sort of colloidal dispersion and just sort of paint on a device, and you want that thing to have a band gap for all sorts of really cool applications that a band gap has, then you would do well to have a quasicrystal in that case. You do better than if you have a crystalline structure. There's an open question, which is whether or not three-dimensional quasicrystals have band gaps. That's not known. Very strange and interesting nonlinear behavior, and they have sort of surprising effects, such as disorder-enhanced transport. So even though quasicrystals are metallic, they're not very good conductors. But it turns out that if you anneal them more poorly, so that, in other words, you don't do a very good job of actually making the quasicrystal, then their conductivity goes up, which is very strange. That doesn't usually happen in ordinary materials physics. So they have all these strange and interesting properties. The eigenstates are best described as fractal-like. So here's just a few snapshots of eigenstates of a quasicrystal. They're neither fully extended nor localized like an Anderson localization. They are best described as power law-like, self-similar eigenstates, a very strange spectrum. They have these fractal-like spectrum that, at least in the case of one-dimensional Schrodinger equations, one-dimensional quasicrystals have been shown to be Cantor sets. So this is the kind of system that we are interested in. If we take a Penrose tiling in the plane and make it into wiggly waveguides, can we have these topological states? You know, we don't have all the normal mechanisms of topological physics for quasicrystals. Usually, in every realization of a topological insulator that I know of, you start off with a Dirac cone. You actually have to have that Dirac behavior, you have to have that touching in order to get the topological edge states to begin with. You know, we don't even not have Dirac cones. We don't even have K. We don't have dispersion. And yet we have found these topological edge states actually exist. So here's a plot of the quasicrystal density of states as a function of the strength of that gauge field. And what you find is that there are band gaps in there that actually can be identified as topological. They open and close. Why is this one topological and why is that one not? I don't know why, but we can quantify it and say which one is. And we see these edge states live inside. So here's some simulations of those topological edge states in quasicrystal, and you see them just propagating around chirally in the system. And this is really the first example of states in quasicrystals that are extended throughout the whole system. They usually have power law decay, but because of the nature of these topological states, they really have to be extended completely along the edge. So this is just, you're seeing time dynamics here. This is the actual wave packet propagating along, but if you were to look at the corresponding eigenstates, they would be extended along the full edge. Completely extended states, completely different character.
So you produce a defect on the edge for there, or they'll just behave the same way?
They would.
If you introduce a defect along the edge,
yes.
Is the behavior the same?
The same. It's funny because there are going to be a lot of questions on the videotape that are going to sound a little bit like repetitive or something. Yes, so I don't need this. So the answer is that yes, they absolutely would. We didn't do that simply because effectively kind of everything is a defect in a quasicrystal in some sense. I mean, you can create a defect if it doesn't come directly from the quasicrystal pattern, which is precisely defined. You could take out a waveguide, for example, and they would behave like that. We haven't actually tried that. I'm sure.
It seems that it would be important to do because there are edge states in the structures that you have the ordered periodic structures.
We'll open the discussion and questions right now.
Okay, sure.
I mean, there are non-protected edge states as well.
Yes.
And so how do we know that these aren't?
Okay, yes.
Okay.
so the question is, how do we know that these are actually protected edge states? I didn't have to repeat. So how do we know that these, I'll do it for my own benefit. How do we know that these are actually protected edge states as opposed to just trivial edge states that you might see in a honeycomb lattice with not in tight binding, for example? Okay. The answer to that question is that we calculate the topological invariant associated with those gaps. And so that is impossible. It's impossible to calculate the Chern number because you need to integrate over k, and there's no k. So we have to use something called the Bott index, which is an alternative quantifier of actually the difference between Chern numbers of bands that is not dependent on periodicity. So we calculate the Bott index, and that's how we establish with certainty that a given band gap is topological or not. And the dispersion of those states really do cross. When we see the actual edge states, we see them fully cross the gap. So those two taken together tell us that they really are topological. And there's only one direction of the groove velocity as well.